Dear students, today we will be discussing about solar photovoltaic power generation systems. Mostly today we will discuss about fundamentals of solar PV systems and concept of solar PV power plant. Let us discuss the fundamental content. We will have solar cells, then modules, then arrays, and lastly we will have entire PV system. In a single solar cell, if we talk about, it can deliver a voltage of about 0.5 to 0.7 volt and current density of about 20 to 40 milliampere per centimeter square. So, if we give an example, like if we have 100 centimeter square area which is covered by cells, and we are interested about the current to be generated by using this cell area is equivalent to about 2 amps, because it is something like 20 multiplied by, we have 100, this is milliampere, divided by centimeter square multiplied by centimeter square. So, this goes off, and if we convert this milli, so 1 milli is 10 to the power minus 3 amp. Okay. So, that is how we can get it as 2 ampere, right. And as per the calculation, it is found that about 1 to 2 kilowatt hour of energy could be produced from a 1 meter square area which is covered by cells, right. But these single cells cannot be used for power generation, because this output of the cell is very small and it requires protection against dust, moisture, mechanical shock and outdoor harsh environment. The workable voltage and reasonable power is obtained by interconnecting many cells in series and parallel combinations, right. So, if we do so, then what we can configure is nothing but a module. So, you can see here different cells are connected in series and parallel. In most of the cases, it is found that this minimum number of cells considered in a module is about 36. So, as I said before, a single cell can deliver an output voltage of 0.5. So, 0.5 multiplied by 36 cells, then it will be about 18, right, 18 volt. So, the modules are designed in such a way that a single module is capable of charging one 12 volt battery, right. So, that is the logic behind it. Of course, there are big modules nowadays, we can have about 325 cells or maybe 325 watt from a single module. So, that way we can calculate the number of cells required, and sometimes bigger size modules are also available in the market. And if we are talking about big power plants, then we need to connect many modules in series and parallel based on the requirement and capacity planned, right. So, that is how it is shown. There are many modules which are connected in series and parallels. Now, if we talk about PV system, so what are the component comprises of a PV system? So, firstly we need the solar arrays, which are combination of many solar modules. Then we need tracking system, because we need to track it so that we can maximize the solar radiation conversion to energy, that is usable energy. We need mountings, because we need structure. Without structure we cannot hold the heavy solar modules. Then proper cablings, it may be AC cabling and DC cabling, because when the energy has to carry from solar modules to the inverter, then that is DC, and then after inverter it will be AC cables. Then we need DC insulator, then generation meter, surge controller. If the system is having batteries, then we need surge controller, because this is primarily used to protect the life of a battery. Then a battery is inverter, which converts DC power to AC power, then fuse box, then AC isolator, then electricity meter. So, these are the primary components which are required for a PV system. Now, let us have a look about the different materials used as solar cell materials. We can have single crystal silicon solar cell, multicrystalline silicon solar cells, amorphous silicon solar cells, gallium arsenide cell, copper indium, which is gallium, and diselenide cells, then cadmium telluride cells, then organic PV cells. So, we can also see the classification and its conversion efficiencies here in this chart. So, primarily it is classified into 3 groups: silicon semiconductor, compound semiconductor, and organic semiconductor. So, under silicon semiconductor we will have crystalline and non-crystalline silicon cells, and then again we can subclassify under crystalline is single crystal and polycrystalline, and for non-crystalline we will have amorphous. So, the kind of cells we use in calculators, it is nothing but it is a amorphous silicon solar cells. And if we see the conversion efficiencies, single crystalline silicon cells are having higher conversion efficiencies compared to polycrystalline or multicrystalline silicon cells. Apart from that, when we are interested about compound semiconductor, what we can see, it is a gallium arsenide having very high efficiency, but this material is not so abundantly available. So, that is the reason why this material has not gained that much of popularity as the silicon based solar cells has gained. So, in the market, is today's market, if we talk about, more than 90% solar cells are silicon based solar cells. Under organic semiconductors, we will have dye sensitized type or organic thin film type. So, we can see the efficiency of these categories are low compared to the other solar cells. How do you estimate the conversion efficiency? For this, we need electric energy output to the energy of the insolation on cell. So, that means we need the intensity of the radiation multiplied by the area, and then we need some electrical devices to monitor the output. Okay. This is output. It may be P, which may be V into I, right. Now, the chart what you are seeing here, it represents the historical development of solar cells with its efficiencies. You can see the large development, but it slowly is gaining the popularity for many of the solar cells, but there are solar cells like perovskite solar cells, it jumps like frog jumping, its development is going very fast. And what other development is going on is like combination of different band gap material in tandem in order to achieve higher efficiencies. What they do in those tandem cells, they will have multiple layers of maybe perovskites with multiple layers of silicons. Okay. What will happen if they make these multiple layers? So, for example, if we use perovskites is one condition, then these perovskites harvest blue light while the silicon picks up red and infrared wavelength. That is how they can increase the amount of energy which is falling on the substrate, and that is how we can achieve higher conversion efficiencies. for this kind of configurations, it is found that they can go up to an conversion efficiency of 32.5%. And this is, we can take it from sources like how development is taking place and how the different group of people at different countries developed the cells historically. Now, let us pay attention about the crystalline, polycrystalline and amorphous structure. So, this structure is crystalline and middle one is polycrystalline and last configuration is amorphous. What happen in case of crystalline solids? These atoms and molecules here or ions are arranged in a highly ordered microscopic structure and forming a crystal lattice, as you can see here, that extends in all directions, that give unique properties, particularly mechanical, optical and electrical. And opposite things happens in case of amorphous structure. The cells are very unorganized. The atomic position is limited to short range order only. But in case of polycrystalline, you can see it exists between two extremes like crystalline and amorphous, and it is made up of a number of smaller crystals which are known as crystallites and paracrystalline phases. So, by looking also we can see like what are the structure. So, by looking the structure we can confirm whether it is crystalline, polycrystalline and amorphous structure. Now, let us learn the IV characteristics of a PV cell, then we will go for the modules. So, like how we can draw these IV characteristics. So, in the vertical axis I am representing I and horizontal axis is V. So, normally what happens with increase in voltage, current is almost constant to a values and then it decreases and reduces to the 0. Okay? The intercept of this axis, this is maybe x axis and this is maybe y axis. So, this is VOC and intercept of y axis is ISC. This is short circuit current and this is the open circuit voltage, right. In the same plot we can draw the power versus voltage. So, if we are interested about power versus voltage, then how will look like. So, it will go linearly, it will increase and it will reach a peak, then it will come and reduces to a value 0 at VOC. Okay. Fine. So, this is nothing but Vm and this is nothing but Im. Okay. That means, the closeness of the characteristics curve or the closeness of the characteristics to the rectangular shape is a measure of the quality of the cell. That means, an ideal cell would have a perfect rectangular characteristics, right. So, this is PV curve and this is IV curve. Okay. We can draw it in scale as well, because we know the current density and then VOC of say silicon solar cells, at the same time we can calculate what will be the power. So, this is power, right. Also sometimes we are interested about this connection of cells in series and parallel. So, this is volt and this is in amps or amperes. Okay. If we consider two cells which are to be connected in series and then in parallel. Okay. So, if we have to connect the cells in series, that means what will happen? So, we are increasing the voltage, and when we are connecting the cells in parallel, that means we are increasing the current, right. So, if we make a IV characteristics curve something like this. Okay. So, this is in series and we can have MPPT here, and if it is in parallel, this will be something like this. Okay. This will be something like this. So, if it is V here up to V up to this point, then this is also V. This entire section from here to here, it is 2 V. Okay. And if it is I and this is I, and for entire section it will be twice I. That means, when we are connecting the cells in series, that means we are increasing the voltage, and when we are connecting the cells in parallel, then we are increasing the current, right. Also, we might be interested about a term called fill factor. This fill factor of the cell is defined as F is Vm multiplied by Im to the VOC multiplied by ISC. We expect that each value is close to unity, but it has never been unity. For silicon based solar cells, its value is about 0.5 to 0.83. Okay. And once we know this, we can also calculate the instantaneous efficiency. So, this is represented by eta I, which is equal to Vm multiplied by Im to the amount of radiation received, this may be IT, and then area of the solar cell. Okay. And this Vm Im can also be expressed in terms of VOC ISC, right. So, that means, if we write the instantaneous efficiency term in terms of VOC ISC, then it will be something like FF multiplied by VOC multiplied by ISC divided by IT into AC. Okay. So, that is how we can find out the values of instantaneous efficiency, right. Now, let us move to the equivalent circuit diagram of a solar cell. Before we move to the equivalent circuit diagram, let us also see like how this current which is generated when solar radiation falls on a solar cells is sensitive to size of the cell and the solar radiation. So, what you can see here, this is IV characteristics curve at solar radiation say I1, and this may be at I2. Okay. So, I2 is greater than I1. Okay. So, that is how it appears something like this. and when intensity is more, then we will have higher ISC value. So, we will have this kind of things. Okay. That means, this ISC is very sensitive to cell size and solar radiation. If we increase the cell size and the solar radiation, then it is expected that we will have higher short circuit current. But how to increase the open circuit voltage? We need to think about its material, right. So, that we need to concern about material properties, right, to look into the matter of open circuit voltage, right. So, that is how it is said that solar cell output power increases with increase in solar radiation. And also we have seen the changes in the short circuit current are essentially proportional to the change in the solar radiation. However, changes in voltage are comparatively less, what we can observe in this plot. And maximum efficiency, what we can define the ratio of maximum useful power to the incident solar radiation, which can be expressed in terms of FF, is presented here as well. So, for an efficient cell, it is desirable to have high values of fill factor, short circuit current and open circuit voltage. The high value of short circuit current are obtainable with low band gap material, while high values of open circuit voltage and fill factor are possible with high band gap material. So, we have to make a compromise how to increase the efficiency of solar cell. Now, let us learn about the equivalent circuit diagram of a solar cell. So, what you can see here, there is a current source. So, amount of current which is generated by the source is ISC, and this is the PN junction, and IJ represents the junction current, and this is the shunt resistance, internal shunt resistance, and RS is the internal series resistance, RL is the load resistance, I is the current which flows through the load resistance with a potential of V, right. Normally, this RHH value, which is shunt resistance, is very high compared to the load resistance. Again, this internal series resistance is very low compared to the load resistance. That is why there is no heat dissipation, and current I, which is flowing through the circuit, is flowing through the load resistance. So, if we have to quantify the amount of resistance in case of shunt resistance is about 200 ohm to 300 ohm, and series resistance is 0.05 ohm to 0.1 ohm. So, we can simplify this equivalent circuit diagram to something like this. It is considering the shunt resistance is infinite and series resistance is 0, right. So, this is the equivalent circuit diagram now. There is no shunt resistance component and series resistance component here, considering these facts. Okay. Now, let us show how theoretically you can calculate the maximum power developed by a single cell. What we have discussed before, for IV characteristics curve, we can generate the curve by using a electrical system, but the same thing we can demonstrate with the help of this mathematical approach. So, the load current at fixed values of temperature and solar radiation, we can write the expression something like I is equal to ISC minus I naught exponential EV by KT minus 1. So, what is I naught here? I will write here. I naught is the dark current or reverse saturation current. Reverse saturation current or dark current. And what is E here? E is the charge of an electron. And its value is 1.602 into 10 to the power of minus 19 joule per volt, and K is Boltzmann constant. Boltzmann constant, and its value is 1.381 into 10 to the power of minus 23 joule per Kelvin, and T is the absolute temperature, in Kelvin, and ISC is the short circuit current. Okay. And I is the load current. So, this I naught is reverse saturation current or dark current. How this is happening? This current flows even though these cells are not exposed to solar radiation or light source. Okay. So, now if we are interested about open circuit voltage, that means I is 0, there is no current flowing in the circuit. So, under that condition, if we substitute this value, then what we will have? V is equal to VOC, right. And again, if we substitute in equation number 1, then we will get an expression of VOC, which is nothing but function of ISC I naught of the cells, right. And then if we are interested about power which is to be developed by the cells, can be expressed as P is equal to I into V, right. So, this is the expression for I, and we multiply with V, and also we know the variation of power versus voltage. It is something like this. It reaches a peak here. So, at this peak dP by dV will be 0, right. So, at this condition, what parameter we calculate, that will give you the maximum values of Vm and Im. Okay. So, once we know Vm and Im, then we can calculate what is P max, okay, and also we can calculate the other parameters. So, now let us write down the expression without deriving all the steps, like we will have, since dP by dV is 0, then we can differentiate the power expression. Then what we will have is something like 0 is ISC minus I naught P multiplied by E by KT exponential of EV by KT plus exponential of EV by KT minus 1. Okay. If we do rearrangement, then what we will have is something like ISC by I naught plus 1 is equal to exponential of EV by KT, EV by KT plus 1, right. And here what we can write, this V is nothing but V max or Vm, right. So, this expression we can write again, it is something like ISC by I naught plus 1 is equal to exponential of EVm by KT, then EV by KT plus 1. Okay. We can also calculate the Im, and if we do the intermediate steps, then what we will have, Im by I naught will be something like EVm by KT, then EV by KT plus 1 multiplied by ISC plus I naught divided by I naught. Okay. Then we can find out the maximum current Im is something like EVm by KT divided by EV by KT plus 1 multiplied by ISC plus I naught. Okay. And we can calculate the maximum power as well. Maximum power Pm will be something like Im multiplied by Vm, which is equal to E Vm square by KT divided by E Vm by KT plus 1, then we will have ISC plus I naught. Okay. So, this is how we can calculate the maximum current and maximum power. So, this is numerically we have calculated, and this can be compared with the experimental results, right. Now, let us discuss about the effect of solar cell temperature on the solar cell efficiency. So, if we visualize something like that solar module, it is something like this. If we visualize a solar module, it will appear something like this. It is glass, then we will have EVA, then we will have solar cell, then we will have again EVA, then Tedlar. So, we can like this is glass, then we will have EVA, thiolvinyl acetate, then PV cell, then we will have EVA again and Tedlar. Okay. So, these many layers are composed of a module, right. So, when say this is okay, this is a cell and solar radiation is falling on the cell, and then what happens? It will generate electrical energy, right. And then some radiation will move through the cells. Okay. So, it will generate thermal energy. Okay. And also this thermal energy will contribute in increasing the temperature of the solar cell, rise in temperature. So, if this is happening, that means we are losing the efficiency. okay, and other sides heat losses will take place, right. This is how this energy transfer takes place in a cell, right, and this temperature of the cell determines the electrical performance of the cell. Okay. That means, if cell temperature increases, its efficiency decreases significantly, right. So, for unit area, the energy balance can be written as alpha tau I t is equal to eta c I t plus u l T c minus T a, and here tau is transmissivity of the cover of the solar cell, transmissivity of the cover of the solar cell. Alpha is the absorptivity of the solar cell, eta c is the electrical efficiency, and u l is the overall loss coefficient. So, it may be side and bottom, or maybe top, then bottom, and sometimes side as well. And T is the ambient temperature, and T c is the cell temperature. Okay. So, this is the amount of radiation which is falling I t. So, now if we are interested about the no load condition, then what will happen? Okay. For no load condition, the C will be 0, that means electrical efficiency is 0, because no utility is attached during the time. So, if this value is 0, then this equation 1 implies alpha tau I t is equal to u l T c minus T a. Okay. Or we can further simplify alpha tau divided by u l is T c minus T a divided by I t. Okay. This is actually NOCT, and this is also NOCT. What is NOCT? Is the nominal operating cell temperature, which is nothing but the temperature of the solar cell corresponds to 20 degree Celsius, 800 watt per meter square irradiance, and 1 meter per second wind speed, and at no load condition. So, if this is the condition, then we can write this expression, and also we can find out the cell temperature. So, we have to use the equation again if we are interested about the cell temperature. The cell temperature, which can be calculated something like alpha tau, then we have I t, then this is something like minus, then we will have the C I t is equal to U L T c minus T a. So, T c will be something like T a plus alpha tau by U L and 1 minus eta c alpha tau is I into T. Okay. So, this is the expression for cell temperature, right. So, we can also find out the electrical efficiency, which is a function of temperature. So, let us write this expression as well. So, this NOCT has already defined here is the nominal operating cell temperature, which is nothing but the temperature of the cell or solar cell corresponding to 20 degrees C, 800 watt per meter square, solar irradiance and 1 meter per second wind speed and at no load condition. Okay, that is how we can define what is T c at NOCT, right. So, if we are interested about electrical efficiency, which is a function of temperature, we can write E E is nothing but eta naught 1 minus beta naught T c minus 298, okay, where eta naught is electrical efficiency of the solar cell, under standard test condition, and beta naught is the temperature coefficient for silicon cell. Its value is about 0.0045 Kelvin inverse, and T c is the solar cell temperature. Okay. So, this is the expression of electrical efficiency in terms of temperature, right. So, this is important while calculating the solar cell temperature, because see this solar cell or module, if we touch the back side, so that temperature is different than what is no exact solar cell temperature. So, that we must have to calculate, then only we can design the other approaches for cooling the PVs and all. So, let us now discuss how this solar cell efficiency decreases with temperature. So, in this phenomenon what happens, for example, if we consider two different silicon based solar cells, crystalline and amorphous, you can see how efficiency of the cell is decreases with increase in the operating temperature. Okay. So, it is said that this decrease is about 0.4 to 0.5% per degree increase in temperature in case of crystalline silicon cells, and for amorphous this reduction in efficiency is not that much as in the case of crystalline silicon solar cells. So, it is about 0.25 degree per degree increase in temperature. So, one more plot we can generate. This is IV characteristics curve at normal temperature and at high temperature. So, by considering the fixed insolation, if the temperature is increased, so the red color indicates the increase in temperature, there is marginal increase in the ISC value, and this is due to the reduction in band gap, which causes increase in photogeneration rate, but a significant reduction in cell voltage can be seen when there is a increase in temperature, right. So, why this is so? This happens because this reverse saturation current increases rapidly with temperature. It is about 2.2 millivolt per degree Celsius, and as a result of which fill factor decreases, and that is how we need to do some arrangement which can reduce the temperature of the solar cells. Finally, that will augment the efficiency of the solar cell or module, right. So, now let us classify the modules. Primarily, it is classified into two groups. One is glass to Tedlar and other one is glass to glass or semi transparent PV modules. So, if the back cover of the module is made of opaque Tedlar, then we called as glass to Tedlar, and if the back cover of the module is made of glass, it is known as glass to glass or semi transparent PV module. The amount of light transmitted from a semi transparent PV module depends on its packing factor. Okay. So, let us now define what is packing factor. So, this packing factor is defined as the area of the cell to the area of PV module, right. So, once we are done with this, we might be interested about efficiency of the PV module. So, if we are interested about efficiency of the PV module, it is represented something like EM is tau z packing factor multiplied by electrical efficiency of the cell. Okay. So, here it is something like, if we consider this module and this entire module is covered with the cells, okay, no other gaps are present, then its packing factor will be 1 as per the definition, like area of the solar cell to the area of the PV module. That means, this module is covered by entirely with cells. Okay. So, under that condition, this expression 1 reduces to eta m tau z then eta E, right. That means, now we can say the efficiency of the cell, which is represented by E, is always more than the efficiency of the module, because we need to consider this transmissivity of the glass cover, right. Also, we can express this expression in terms of fill factor multiplied by ISC multiplied by VOC divided by AM then and this is AC multiplied by IC or maybe IT. Okay. And if we write the temperature dependent electrical efficiency of the module, temperature dependent electrical efficiency of the module, it will be something like MO multiplied by 1 minus beta naught Tc minus 298, right. So, this is nothing but electrical efficiency of the PV module, electrical of the PV module under standard test condition, right. This is cell temperature and this is the temperature expansion values, which is nothing but 1 by T. Okay. So, that is how we can calculate the temperature dependent electrical efficiency of the module, right. Now, let us learn what is series and parallel connection in PV modules. So, we had already discussed about series and parallel connections of solar cells. So, now the case of modules, okay. The same thing, if we have to connect the modules in series, say for example, if we give some scale, so this is 0, this is 0.3, this may be 0.6, maybe we have 0.9 here, then 1.2, then 1.5, then we have 1.8 and maybe this is maybe 3, then we have 6, we have 9, 3, 6, 9, and this is current. This is voltage, right. So, for series connection we have to have this kind of connections, it will be 0.6, then we will have 1.2 if this is something like this, and this is something like this. That means, VOC is 0.6 volt we have considered. So, this is VOC and this is 2 VOC and this is 3 VOC. So, 3 modules are connected in series and this is ISC, this is 2 ISC and this is 3 ISC. That means, 3 modules are connected in parallel. This is parallel and this is series. And we can also see something like if you have this cell, cell 1, not cell, this module, this is one module and this is one module. So, these are connected. So, this is cell only we are showing here, but same thing it will be there, because one cell will produce 0.6 volt, okay. And when the cells are connected in parallel, then things will be something like this. Same connections what we have discussed for cells, again we are drawing for 3 and this is at 6 volt, right, and this is series and this is parallel. Okay. And this is the specifications of a module. So, primarily we need to specify all those parameters like module size, module weight, cell size, number of cells, nominal output power, nominal voltage, maximum voltage, then VOC, ISC and then conversion efficiency. Also we need to specify what is standard test condition. This intensity is 1000 watt per meter square, AM 1.5 spectrum and cell temperature of 25 degree Celsius. Now, let us discuss some of the interesting aspects of solar modules. Like when these cells are to be connected, then what are the problems might arises. First thing is cell mismatch in the module. So, what will happen if cells having different characteristics like different values of ISC, VOC and FF, then what will happen finally to the module. So, these aspects is very important. Then effect of shadowing, then partial shadowing of cell when cells are connected in series, partial shadowing of cells when cells are connected in parallel. Then these two conditions we need to discuss. For cell mismatch, this VOC, ISC, VM, IM of all the cells must be exactly same. So, any mismatch in the characteristics of these cells leads to additional mismatch losses. Normally what happens, this P, which is the combination of all the cells, always less than the sum of the individual cell peaks. Ideally it should be equal, but this is not equal, some losses will be always there. So, in one case when two cells with mismatched characteristics are connected in series and the load is applied, both the cells are bound to carry the same current. This is very important. And in case 2, when two cells with mismatched characteristics are connected in parallel, the voltage of the cells are bound to be equal. Okay? And also this larger the number of modules, more would be the possibility of quantum of mismatch losses. So, that is how we need to have optimized number of cells in order to have maximum power conversion and loss minimization. So, these phenomena are shown in this plot, like two cells and these cells are connected in series, then what will happen to the voltage sense. And how to reduce the mismatch losses? Modules are fabricated from the cells belonging to the same batch and cell sorting is to be carried out to categorize cells having match parameters with specified tolerances. About shadowing, the partial shadowing can have significant consequences for the output of solar modules. The current generated by shaded cell is significantly reduced. So, for example, if these cells are connected in series and this cells is covered with leaf, that means shadowing effect shadow is falling on these cells, then what will happen? This current generated in these cells will be very, very less, but when we are discussing about the power generated, this circuit will take the minimum current, even though other cells are generating the rated current, but the circuit will consider the minimum current which is flowing through these shadowing cells. Okay. In a series connections, the current is limited by the cell that generated the lowest current, and this cell dictates the maximum current flowing through the modules. That is the primary problem. So, power generated by the circuit will be very, very less. The shadowed cell does not generate energy, but starts to dissipate energy and heats up, which leads to decrease of PV output, and this can be prevented by installing bypass diode in an appropriate manner in the module, right. You can see now these are the diodes which are connected. Okay. So, if something goes wrong with one cell, then this will be discarded and rest system will operate, and we can have higher values of energy conversion. And when cells are connected in parallel, the partial shadowing is less of a problem, because the current generated in the other cells do not need to travel through the shaded cell. Okay. Combining the cells in series and by using bypass diodes is much better option to do. So, for your understanding, one bypass diode for every 18 crystalline silicon solar cells is provided. If we have 36 cells, then we may require 2 bypass diodes in the terminal box to control the system. Again, we will have series parallel connections of modules with blocking and bypass diode. So, in parallel connections, blocking diodes are connected in series, so that if any string fails, the power output of the remaining series strings will not absorb by the failing string. The bypass diodes are installed across each module, so that if one module fails, the output of the remaining module in a string will bypass the fail module. In modern PV modules, these diodes are internally embedded. Okay. So, that is how what module we can see, these are very, very smart modules. So, you can see here the installation of blocking diodes and bypass diodes. Okay. These are the cells. Now, let us pay attention about solar PV output maximization. So, how we can maximize the solar PV output? By mechanically tracking the sun. So, we can have some device and we can track the sun, okay, or we can have some kind of electrical arrangement by manipulating the load to maximize the power output under changing condition of insolation and temperature. And that is how we can have one electronic control system called maximum power point tracker. In shorts, we call it as MPPT. Okay. So, we can install an MPPT and MPPT will take care of this maximization of electrical energy conversion, right. Also, we can think of load matching. The operating point of an electrical system is determined by the intersection of source characteristics and load characteristics. So, you can see these are the characteristics lines and these are the intersection point. Okay. So, there are different loads are connected. So, if we can match it properly, or you can see these three systems. So, this will operate at maximum power point. That means, we can utilize the power very effectively. So, by doing some load matching, we can have access to the maximum power point. So, this MPPT, the maximum power point tracker, what we can do, we can have this kind of configurations. So, we can have IV characteristics, IV, and there might be of different this kind of plots. Okay. And this might be the maximum points, and solar radiation is increases. This is I, intensity of solar radiation in increasing order. This is increasing order. And there might be of different loads, maybe we have batteries, maybe fans, or maybe resistor, maybe fan, maybe resistor, or maybe batteries. Okay. This IV characteristics keeps on changing with insulation and temperature, what we understood before. Okay. To receive maximum power, the load must adjust itself accordingly to track the maximum power point. An ideal load is one that tracks the maximum power point. Okay. So, if the operating point deviates significantly from the maximum power point, this is the maximum power point, it may be desirable to interpose an electronic maximum power point tracker between PV system and the load. Okay. So, if we can operate the system at this condition, then we can really maximize the power utilization, right. So, what we can show here, there are three different loads, battery, fan and resistor, and these are operated at different conditions. So, if we can operate the system at this condition, then we can maximize the power what is generated by the PV cells, right. So, this MPPT is an adoption of DC-DC switching voltage regulator, and it is a coupling to the load for maximum power transfer by require either providing a higher voltage at lower current or lower voltage for higher current. And buck boost scheme is commonly used with voltage and current sensors tied into a feedback loop using a controller to vary the switching time. So, this is the configurations where MPPT using buck boost converter. We can have PV, then we have control and sensing and logic and other electrical connections. So, what we are really interested about, the power output of the PV system. So, if we write the power output of the PV system, P is equal to V into I, and if we consider incremental change in power P plus del P, which is nothing but V plus del V multiplied by I plus del I, and if we do the simple derivation, V into del I plus del V into I plus del V into del I. Okay. So, if we ignore this term, this is very, very small term, okay, and yeah. delta P is something like del V into I plus V into del I, okay, because del P must be 0, as del P must be 0, at peak point. Okay. So, here P plus del P, so this is something like P into V I, this is gone, this part is gone, okay. This two will be remain, fine, ignoring the small terms, and our expression can be of something like this, dV, I can write dV by di, which is nothing but minus V by I, okay, at the peak point, because our thing should be something like this. So, I am talking of this point, this is P, this is V. Okay. So, this term, this part we can name as dynamic impedance, and this term is static impedance. Okay. So, now let us learn the strategies how this can be operated, right. So, what are the different strategies? So, number one is by monitoring the static and dynamic impedances, okay. By monitoring static and dynamic impedances. Okay. That means, a small signal current is periodically injected into the array bus, and the dynamics or dynamic as well as the static bus impedance are measured. Okay. So, the operating voltage is then adjusted until the condition is something like ZD is equal to minus ZS. That means, dynamic impedance equal to the negative sign of static impedance, right. And second condition is by monitoring power output, It is something like, already we know dP by dV, right. In this plot, at this point, this dP by dV is 0, okay. And if we come, what will happen? If we go from this point, then what will happen? Okay. So, voltage is adjusted and power output is sensed, right. So, now what happened? Operating voltage is increased as long as this voltage is increased as long as dP by dV is positive, right. So, dP by dV is positive as long as this is positive, voltage will be increasing. Okay. Then, if dP by dV is sensed negative, then we need to decrease the operating voltage, right. And this voltage is unaltered when dP by dV is 0. That means we need to fix at this point. Okay? We need to increase the voltage if it is positive, if it is negative we decrease the voltage, and voltage remains constant at dP by dV condition, at dP by dV is 0, right. This is the second strategy, and third strategy is by fixing output voltage as a function of VOC. Okay? It is something like Vm by VOC is K, okay? Or you can write Vm can be calculated by K multiplied by VOC. Okay? So, for high quality crystalline silicon cells, the value of K is considered to be 0.72. So, it is very easy to control this, because it is something like Vm is equal to 0.72 multiplied by VOC. That means the operating voltage of the array is then set at K times the VOC. Okay? So, these are the three strategies normally adopted for this MPPT. So, now let us discuss about the arrays. So, once we have done with the cells and modules, then we can couple the modules in series and parallel as per the requirements. If we use many more modules, then it becomes arrays to meet the demand, okay, as per the need. So, when we are talking about solar PV systems, it might be central power station systems or it may be distributed systems. So, under distributed systems we will have standalone system, grid interactive systems and small system for consumer applications. So, standalone system may be street light or maybe small electrical requirements, and for grid interactive system the system is connected to the utility grid with two-way metering system, and it may be a small rooftop system or a relatively bigger system meant for whole village. Small systems for consumer applications includes the systems which are meant for low energy consumption or low energy consumer device requiring power in the range of microwatt to 10 watt. So, these are some of the applications of standalone system like water pumping, street lighting, medical refrigerator, telecommunications and signaling, remote refrigerator. These are some of the photographs of the devices. So, in this lecture primarily we are trying to give you an idea about the fundamentals of PV cells, modules and arrays, and how to calculate power and efficiency of a solar cells, and the concepts of solar PV power plants. I hope you have got an idea on solar PV systems and power plant. In the next class, we will be primarily discussing about the design and analysis of solar standalone PV systems. Thank you very much for watching this video. Thank you.